Welcome. Today we will discuss advanced ceramics and its raw materials. This is Sabyasachi Roy from And Ceramics. In our last videos, we have seen many definitions of ceramics. The ceramics are non-metallic inorganic materials that are formed by application of heat and sometimes by heat and pressure and are insoluble in water. So we can say that these are inorganic non-metallic solids comprising of metals, nonmetals and metalloids atoms primarily held in ionic or covalent bond. Ceramics assisted human civilization to grow. The processing has started before 10,000 BC. Initially, human made everything with ceramics. Later, with advancement of civilization, metal and polymers were discovered and invented. Still, many ceramics has been invented and developed for many advanced ceramic applications. Later, we will see classification and development of ceramics as per different application. The ceramic safe forming processes are different kind of processes followed in industries. The initial processes are dry shaping, plastic shaping, and semi-liquid shaping. So in dry shaping, we can see that there are two kind of pressing process is adopted. One is dry pressing, that can be uniaxial or biaxial. There will be isostatic compaction in which the processes can be dry bag isopressing or wet bag isopressing. In plastic shaping, the mass of ceramic will be much plastic and it can be extruded or injection molded into the dies as per the shaping requirement. There are processing of joining and jiggering which is used to manufacture mainly the insulators. Also, the third process system is semi liquid shaping in which the process is to make a slurry and then it is being slip casted or direct coagulation casted, freeze casted, gel casted or tape casted. So these are the different processes, except that there are also some processes like vibrocasting by which people manufacture different kind of ceramics. We will discuss in detail the processing of ceramics in later videos. In our day to day life, we see ceramics everywhere from sanitary ware, tableware to our glass, home, cement, tiles, insulators, even watches, and many more applications, advanced ceramic applications like magnetic ceramics, the DRAs, the ceramic seeker cones, radomes, etc. In this world of materials, we define and classify materials in many categories. In broad respect, we can classify materials in three categories like polymers, metals, and ceramics. Ceramics can be divided into three categories like hydraulic cements, glasses, and ceramics, advanced ceramics. The cement, lime, and plasters comes under hydraulic ceramics. Similarly, in glasses, we can divide into some different categories like binary CNS glasses, silicate based glasses, non silicate glasses. Non silicate based glasses can be divided into many other categories depending on its constituents like B2O3, P2O5, or arsenic oxide. The advanced ceramics component is mainly divided into, or ceramic components can be divided into advanced oxide ceramics, advanced non oxide ceramics, and classical silicate ceramics. Classical silicate ceramics can also be divided into mainly alumina based, silica based, or calcium magnesia based ceramic components. The oldest evidence of using ceramics were found as earthenwares before 30,000 BC. There were several applications of ceramics in day to day life at that time. Later, people developed a lot of ceramic materials for a long time, and those were very important aspects of human civilization. Like people found out how to make their buildings, they found out how to use lime, mortar, plastics. They also invented glass, they started manufacturing porcelains, and there are many other developments happen at that time. The development has been slowed down after the invention and discovery of metals in the time of 1000 AD to 1800 or 1900 AD. Then there was a rapid development of ceramics for application in many advanced technological areas like from spark plug, glass fibers, insulations, optical fiber, magnetic ceramic applications, semiconductor applications, superconductor applications, and it is increasing day by day. So now we will see different properties and comparison of ceramics with other materials. Materials in broad respect can be categorized in three parts: metals, ceramics, and polymers. Ceramics, density wise, are lower than metals but higher than polymers. Ceramics are very important material from point of view of application at high temperature because they have very high melting point. These are very unreactive, they have very high elastic modulus, but ceramics are brittle. Metals and polymers have the advantage of ductility in different application than ceramics. So let us look at the property charts of different material. If we look at the property chart of different materials, then we found out that ceramics have extremely high hardness, extreme high elastic modulus, very high temperature strength, and low thermal expansion. These have very good corrosion resistance and resistance to wear, but it has a poor ductility and it has a low density. The beauty of ceramics is that it has a varied range of electrical conductivity to thermal conductivity. Ceramics can be insulators, ceramics can be semiconductors, ceramics can be metal type conductor. So these are very important properties which make ceramics as a versatile material for use in different applications. Let us see the classification of ceramic materials. Based on the engineering applications, ceramics are classified in two broad groups. One is traditional ceramics and advanced ceramics. Traditional ceramics are those ceramics which are mostly silica based components or prepared from natural raw materials like bricks, tiles, sanitary wares, porcelains, and also ceramics with other different kind of components like alumina, magnesia, which are in application of electroceramics like insulators or industrial ceramics. But advanced ceramic components, what we say, do require much higher quality or purity of raw materials, where careful control of this raw materials and processing techniques gives well defined microstructures. So microstructure control the proper properties Like all these applications of dielectric ceramics and magnetic ceramics or optical ceramics, so those were controlled by their microstructures, which were monitored by the processing parameters and raw materials. These are made up mainly high purity aluminum oxide, zirconium oxide, titanium oxide, or different kind of raw rare earth element oxides or non oxides. When ceramics are classified based on applications, there are two forms. One is traditional ceramics and advanced ceramics. In traditional ceramics, we keep whitewares, earthenwares, structural clay products, bricks, tiles, abrasives, refractories, cements, etc. In advanced ceramics, we define it in two different parts. One is electroceramics and another is advanced structural ceramics. In electroceramics, the applications are like electronic substrate or packaging ceramics, capacitors, dielectrics, piezoelectric ceramics, magnetic ceramics, optical ceramics, conducting ceramics, etc. In advanced structural ceramics, the applications are like nuclear ceramics, bioceramics, tribological or wear resistant ceramics, automotive ceramics, or environmental ceramics. So we have seen that advanced ceramics are divided into two categories. One is structural advanced ceramics and another is electroceramics or functional advanced ceramics. Structural advanced ceramics are used for applications where a component or engineering system is subjected to very high mechanical, tribological, thermal or chemical loads, and these are materially like wear resistant ceramics like 92% alumina or 99% alumina, partially or fully stabilized zirconia, cordite, mullite, different kind of spinels, silicon nitride, silicon, silicon carbide, boron nitride, boron carbide, titanium nitride, titanium carbide, titanium boride, etc. Functional advanced ceramics, in contrast to the structural ceramics, utilizes its microstructural effects localized within the volume, at gun boundaries or at the surfaces of conducting and non-conducting ceramics. So these applications are like in semiconducting applications, variesters, piezoelectric, pyroelectric, ferroelectric, and superconducting applications. In the processing of ceramics, when we look at the advanced ceramic processing techniques and traditional ceramic processing techniques, the main unit operations are nearly same. Like these are raw material preparations, forming, high temperature processing, finishing operation, and characterization. Only if you look at the processes like in advanced ceramics, the powders are much more controlled in their purity levels, and these were made by chemically precipitated, and then these are spray dried, freeze dried, or made by sol gel routes. Those were carefully and controlled processings in slip casting or injection molding or hot pressing or hydraulic pressing or rapid prototyping. These were fired generally in controlled atmospheres or proper process controlled electric furnace or microwave furnace or hot pressed, and machined or ground or lapped using laser machining, plasma machining, and ion implantations. The characterization of this different kind of characterization techniques are being followed, like light optical microscopy, X-ray, XRD, ACM, and different surface analytical methods are used to analyze this kind of ceramic advanced ceramic components. While in traditional ceramics, the raw materials are naturally available clay, quartz, feldspar, or silica. These were made by slip casting, potter wheels, jolling jiggering, and fired into flame cleans. And then maximum the finishing happens by glazing or erosion or grinding, and visual checked by visual examinations and optical microscopy. So let us see different ceramic raw materials used in advanced ceramic components and also in traditional ceramic components. There are two type of ceramic raw materials. One is naturally occurring raw materials, another is synthetic raw materials. In naturally occurring raw materials, we use clay, different kind of clay like ball clay, china clay, bentonite, etc. Quartz, feldspar, sillimanite, kyanite, anthracite, bauxite, zircon, etc. In synthetic raw materials, we manufacture fused alumina, high purity alumina, zirconia, titania, silicon carbide, boron nitride, etc. This is a very interesting slide that I got on ceramic raw materials from Slide Slayers. The reference has been given, and they categorize the ceramic raw materials in four different parts. One is crude materials where purity is extremely variable, like shell, stone over clay, tile clay, crude bauxites, crude carnites, natural ball clay, bentonite, etc. Then there is a grade in like industrial minerals where the purity will be 85% to 98%, like ball clay, kaolin, kyanite, bauxite, dolomite, etc. Also, the third category they have mentioned, that is industrial inorganic chemicals, where the purity level will be 98 to 99.9%, like alumina, calcined alumina, which is being made by Bayer process, calcined bauxites, which is being made from brines of seawater, fused alumina, fused magnesia, aluminum nitride, silicon carbide, silicon nitride, barium carbonate, titania, then calcined titanates, then iron oxide, calcined ferrites, zirconia, stabilized zirconia, and calcined zirconates. There are also some special organic chemicals which are more than 3N, that is 99.9%. Various materials are also in alumina, silicon nitride, titanium boride, silicon carbide, boron nitride, etc. In industrial applications, fused alumina plays a very vital role. Brown, brown fused alumina and white fused alumina, these are two important ingredients in many of the ceramic applications. In Bayer process, from bauxite, aluminium metal is being made, and there is an intermediate material, that is processed alumina. So, from bauxite, if it is melted and then quenched and crushed, ground, then we get brown color, brown fused alumina. And from processed alumina, when we melted and crushed, ground to finer sizes, and we get white fused alumina. These have all wide application in abrasives, refractories, and many other technical ceramic components. So in bare process, from bauxite, aluminium is being made. In the bauxite is after mining, it is being crushed, milled, and then the it has been kept into pressure vessel at temperature of 170 to 180 degrees centigrade with sodium hydroxide. In this in the in this section, the alumina reacts with sodium hydroxide and forms sodium aluminate. The rest of the part is filtered out as red mud. Then the sodium aluminate basically added with water, and then aluminum hydroxide crystal is added for oversaturation. Aluminum hydroxide crystallization happened and precipitated out. That precipitate is put into rotary kiln and heated at different temperature to get either gamma alumina or alpha alumina or different kind of calcined alumina. Then the alumina is taken for electrolysis by a carbon anode and carbon cathode, and then the molten aluminum is being extruded or made into sheets or different kind of aluminum alloy or different kind of form of wares. So let us see that how brown fused alumina is being made. Bauxite is mined; those are calcined and then melted in arc furnace, cast and ground in different size fraction, and brown fused alumina is being made. This brown fused alumina is very hard and tough materials with high strength. Is produced by a reduction fusion of high quality bauxite in electric arc furnaces. These are used as excellent and abrasive grain for applications as grinding wheels, sandpaper, blasting media, metal penetration, in many lapping, polishing, and grinding application also. Its thermal properties makes it a excellent raw material for different kind of refractory applications. So, white fused alumina is obtained from fusion of high purity calcined alumina in electric arc furnace. White fused alumina is raw material characterized with high hardness yet friable with high purity, chemical stability, a high melting point, and large crystallite sites. White fused alumina is used in many applications, including grinding and cut-off wheels, refractories, and ceramic shapes, coated abrasives, investment casting, sales, laminates, coating, blasting abrasives, lapping and polishings, and many other applications also. But white fused aluminum applications are different from tabular alumina because tabular aluminas are not so much friable, and those are generally sintered aluminas. These are melted and quenched and crushed aluminas. So these have much more sharp edges and corners, and friability is much more high. So in grinding applications, generally white fused alumina is much more preferable than tabular alumina. High purity aluminas have very high reactivity, very high melting temperature, high hardness, extremely high electrical insulation resistance, and very good thermal conductivity. So these are used in LED applications, semiconductor applications, phosphors, automotive sensors, lithium ion batteries, and many other industrial applications like seals and many other technical ceramic applications. That is why these are in very high demand at present. These are made in different purity levels from 3N to 6N, and the prices also increases abruptly. Like in Indian rupees, if you look at the 99.8% alumina minimum cost around 100 rupees to 250 rupees, while the 99.9% alumina will 10 times off higher than this, and the with the purity the prices increases many a fold. So the high purity alumina is processed through the state of the art hydrothermal technology, generally hydrated aluminas by hydrothermal treatments, and then these are heat treated to make very high purity alumina. Many a times solvent process also being adopted for manufacturing this kind of products. Reduction smelting of premium grade zircon sand and control atomization of melt is used to produce hollow zirconia bubbles, which is being crushed and then it is being graded to different kind of monoclinic or calcium stabilized or magnesium stabilized fused zirconia. The chemically processed yttrium stabilized zirconia and other uh, magnesia or calcium stabilized zirconias are being manufactured from zirconium oxychloride along with the relevant metallic salts, and then those are co-precipitated, and then the co-precipitate materials is heated at particular temperature depending on the requirement of the crystallite size. So these are the stabilized zirconia. Different kind of high purity stabilized zirconia is manufactured by chemical processes. Black silicon carbide is an extremely hard man-made material that possesses very high thermal conductivity and it has a very high temperature strength. It doesn't melt at normal temperature, but instead it generally dissociates at 2600 degrees centigrade temperature. So the typical silicon carbide characteristics are like it has a very low density, high strength, good wear, high temperature strength, like for reaction bonded silicon carbide especially. Reaction bonded silicon carbides are also oxidation resistance, and it has a extremely high thermal shock resistance. And these have good hardness, wear resistance, and good chemical resistance. They are known for their low thermal expansions and very high thermal conductivity. That is why these are being used widely as a clean furniture, and then fast fixed and moving turbine components, silicon carbide seals, pump valves, and heat exchangers, and many applications also found in semiconductor wafer processing. The manufacturing of silicon carbide happens by a solid state reaction between silica sand and petroleum coke at a very high temperature, that is more than 2500 degrees centigrade, which leads to the formation of silicon carbide under the general reaction. Another important advanced ceramic component is boron carbide. Boron carbide has a huge application in thermal neutron absorbers. It is used as a very loose abrasive because of extreme and outstanding hardness. And then also these are being used as a armor plates. So boron carbide is produced by reacting and fusion of boric oxide or boric acid and carbon in electric arc furnace. Thank you. We'll come with many more videos on ceramics and materials and their detailed processings and materials properties. Thank you very much.